share your entire screen. Share. All right, here we go. We are doing bonding. That is this presentation. Here we go. All right. So I will tell you that this chapter that we're starting with is probably one of the more critical chapters of the year. Okay, this one and the next one. You are going to learn starting tomorrow how to write chemical formulas. And if you don't know how to do that basic thing, you're not going to survive the rest of the year. Okay, you'll end up dropping the class partway through second semester. It's kind of like not knowing how to write the alphabet and trying to write a report. If you don't know how to write words, you can't write sentences. And if you can't write sentences, you can't write. Keep going with that. Okay, so you've got to know how to write those formulas in order to put it into an equation. And if you don't get those formulas written right, you're never going to get some of your equations to balance. And if you can't balance your equations, you can't do any of the math that we do second semester. And so it's hypercritical that if you don't understand how to write these formulas coming up in the next few weeks, that you come in and get extra help. And every year, I tell kids this, and every year, people ignore me. And every year, second semester, what do? They have to drop, okay? Because they get too overwhelmed and they can't keep up and they can't write a formula. If you can't write a formula, it doesn't work, okay? So keep that in mind when you are doing this, okay? Sometimes it only takes like 5 minutes for me to sit down and explain something to you, for it to go, oh, I get that now. It's easy. Okay. But if you don't get to that, oh, I get it now, it's easy moment, you're going to have a really, really tough time second semester. Okay. Got it? All right. I will stop belaboring the point. So today we're going to start by talking about ionic and metallic bonding, and then eventually, and I'll touch a little bit on covalent today, but covalent is actually chapter 8. So metallic we're going to start with, and we just spend a few minutes with that, and then we move on to ionic, and then, like I said, we're going to spend some time before Christmas break on that covalent business. So essentially, what you have is, remember you have your periodic table. Oops, why is this not letting me write on here? You're gonna let me write now? Nope, you're just gonna let me click. Of course. Why would anything work on here? Nope, still not gonna work. You're gonna let me write now? Nope. Oh, goodness. This is turned over, right? Huh? Yep, I've tried writing. There we go. Now it's letting me. Okay. No, it wasn't letting me. I tried. Okay, so remember our periodic table. I had you draw that stair-step line over here. Okay. All right. And we said that these things are our nonmetals and these things are our metals, with the exception of hydrogen. Okay. Hydrogen's that goofy one that's over here by itself. All right. So we have a couple different options when it comes to bonding. You can have a metal and a metal come together, and that's going to be metallic bonding. That's this type of bonding. You can have a metal and a non-metal come together, and that's going to be your ionic bonding. And then what would be the third choice? if you had a nonmetal and a nonmetal come together, that's your covalent bonding. And that is chapter 8. We'll get to that in another couple weeks. Okay. The majority of the ionic bonding time is spent showing you how to write formulas for ionic compounds. That's the majority of the time. Okay. And use that time to learn how to do that, because I can't express to you even more. You need to know it. All right. So when we are talking about our metal and metal, we're talking about metallic bonding. Okay. And with this metallic bonding, you end up having these metals forming lattices. And you can think of a lattice almost like kind of like scaffolding. Okay. And you have 8 to 12 other atoms that are surrounding each atom. And because it's a 3-dimensional plane, okay, it's not 2 dimensions, as your paper kind of shows you. It's 3-dimensional plane. They are going to create what's called a sea of electrons. So the sea of electrons is going to allow these electrons to move from one place to another. And remember what electricity is. What is electricity? I've mentioned this a couple times, I believe. Anybody know what electricity is? Huh? Nope. Electricity is essentially moving electrons. You're moving or pushing electrons from one place to another. That's all electricity is. Okay? So with these metals, they're able to push these electrons from one atom to another across. And that's what creates your electricity. With the covalent atoms, they can't do that. And so they don't conduct electricity. This also leads to the ability to move heat across as well. So metals are good conductors of heat and electricity because they have those delocalized electrons. All right. Now, these metals then tend to have high melting and boiling points. Not all of them, but a good portion of them do. They're also malleable. We learned about that in chapter 3. So we can pound them into thin sheets. They're ductile and they're durable. That's why we make durable goods out of them, like automobiles and refrigerators and all kinds of other equipment, like your chair legs, because it's durable. So that when Andrew leans back in it, my chair doesn't fall apart. They are also, did I miss stuff? Do I need to go back? Here? Here? Good? Ready to go? All right. So most of these have pretty high melting and boiling points. Some of them don't. Some of them are lower. Like gallium, for example, will actually melt in your hand. Okay? They're malleable, they're ductile, they're durable. They're good conductors, heat and electricity. Most of them are hard, not all of them. Like you could take a knife and cut through some of them, like I did in that lab that we did a couple weeks ago. They tend to be pretty strong, and most of them are shiny. Just like the alkali metals that you saw when I cut into them and I showed you. I'm like, look, see how shiny this is inside where it hasn't oxidized. All right. We've also talked about these metal alloys. So an alloy is a mixture of elements that has these metallic properties. The properties tend to differ from the elements that they contain. Good? Is there anything? We have two different types. We have a substitutional and an interstitial. Okay, so those are two types. Now, when we say substitutional here, when we talk about something being substitutional, we are typically talking about something that's very comparable to this. So when you want to find a substitute for something, you usually don't find anything that's radically different. Okay, so for example, your parents or grandparents, people you know, might need to have a salt substitute because they have high blood pressure. They're not going to use table sugar as a salt substitute, are they? Because that's not going to taste anything like salt. So salt is actually NaCl. That's your table salt. That's the typical stuff you eat. You can actually go to Woodman's and buy a salt substitute, which is potassium chloride. It tastes very close to this. It's not exactly the same, but if you eat this long enough, you get to the point where you're like, okay, it almost seems normal. Okay. Sort of like people who drink or eat diet food, like diet pop. When they try to drink regular pop, they're like, oh, that doesn't taste right because they've gotten so used to it. So a substitutional item is typically something that's very close to what you're working with. And that's the way it is here with these alloys. A substitutional alloy typically will be similar size to the thing that it's replacing. So sterling silver, for example, has copper and silver in it. They're fairly close, but even better example of that is brass and zinc, or is brass, where you have copper and zinc. These guys are side by side on the periodic table. They are very, very, very close in size. And so it's easy to kind of visualize one of these getting substituted in for the other. Pewter was used a lot back in like the 1700s. You don't really see that as much anymore. But your gold, when you get gold in jewelry, you don't get typically 24 karat gold. Okay? Yeah. Okay, something like that. It's a long time ago. Okay? It's before my, believe it or not, it was before my time.
Impossible.
Okay?
Not Olivia Orton. No, I did not.
But when we are talking about gold, people are like, well, I want something that's 24 karat gold. Well, that's pure gold. And, you know, that's nice when you're talking about like coins or something like that, that you would want to have as far as that. But if you're talking about jewelry, you don't really want it to be 24 karat gold. Okay? There are reasons why. First of all, it's expensive. Second, it's heavy. Okay, gold, I mean, if you look at it on the periodic table, it's number 79. It's heavy. Okay? You wouldn't want to be carrying away around something of that weight and that magnitude. The second thing is that if you get gold that is about the size of my ring here, the band on here, which isn't that thick, but it's, you know, decent enough. If you get gold that's like that, it's very soft. Okay? I mean, think about mercury next to it. Okay? Mercury, yeah, mercury's right next. That's liquid at room temperature. Okay? So they're going to have properties that are somewhat close. Okay? So it's a real soft metal. That's why people can take their Olympic medals and put it under their mouth and they Have you ever seen them bite down on it? They're verifying that that's gold by biting down on it. They can indent it. Okay, it's a soft metal. If I go around and try to do any kind of work around anywhere, that ring's going to fall apart. Okay, so they mix this, like this one's 14 karat gold. That's pretty typical for jewelry, is 14 karat gold. They're going to mix it with another metal and make it more durable. Okay, and that's what they will do with these things. So here's an example of a substitutional alloy, where they're going to go in and they're going to substitute in. And what they do is they melt these two metals down, they mix them together, and then they cool them back down into a solid and use that for whatever purpose they're using it for. Okay. The next one is called interstitial alloy. And what it is these right in between these atoms, these holes here are called interstices. And so what they're going to do is they're going to go through and they're going to fill in those holes with a smaller atom, like carbon. Steel is an example of one of these. So you get to the point where you go over to your social studies class and they talk about the Industrial Revolution. This steel is what drove that Industrial Revolution. When they came up with steel, that was a game changer because they were able to build buildings that were tall. They were able to build air conditioner units because they were stronger and sturdier, and those buildings could support them. So you talk about like economies in southern states, they weren't that great until the advent of the air conditioning because they just weren't as productive. It was just too dang hot to work half the year down there. Okay. And the higher you went in a building, the hotter it got. Steel allowed them to build those taller buildings. It allowed them to build locomotives and different things that didn't rust out all the time. And steel is truly what drove that Industrial Revolution. So when you look at these, this is what happens. You get a smaller atom that's filling this in. That makes these more dense and more durable in the process. And it was that process of doing this where they made, the different types of steel out in Pennsylvania and Pittsburgh and all of those kind of industrial states where they discovered how to do this, that made some of those people really, really rich. But it also allowed other people to be able to branch off and do, amazing things as well. All right. Enough of that with our metals. Now we're going to turn our attention to metals and non-metals. And that's primarily where we're going to sit for a couple days. So let's talk about kind of our forces that hold these together. We've got those two atoms that are being held together. We can do that by a positive nucleus and these negative electrons. That's typically going to be your covalent bonding. That's going to come. And then we have it between these positive ions, which are called what? Cations. Yep, meow. They're positive. Remember that? Okay. And our negative ions, which are our anions. And that is going to be your ionic bonding. And you can remember that because they're ions that are forming that. Okay? Are you positive about that?
I'm not really positive about anything.
Well, as long as it's not COVID, we're good. All right. All right, here we go. We've got valence electrons that we need to talk about because remember, essentially what we want to do is we want to form something with a noble gas configuration. And that we're going to use our electron dot diagrams to be able to keep track of those valence electrons. And they're going to do that. They're going to end up getting this noble gas configuration in one of three ways. They're going to give, as in the form of metals. They're going to take, as in the form of nonmetals. Okay, so that give and take, that is your ionic bonding. Or they're going to share. And that's going to be two nonmetals coming together. And that is covalent. And that is chapter 8. So we will get there. This is what we're focusing on right now. So metals are going to give, nonmetals are going to take, and they're going to do that to get to this noble gas configuration. All right, when we form these positive ions, for example, if we have neon, if sodium gives this guy away, then it's going to have a noble gas configuration like neon. So it just needs to give that one electron away. If it loses one electron, it's going to lose a negative charge. It's going to become positive. And therefore, it is a cation. Meow. See my kitty? Cute little cat, eh? It's positively cute, huh? Uh-huh. Yeah. I try to make it exciting.
Oh. Never a dull moment, Libby. Never a dull moment.
Andrew's over there shooting me.
He shoots everybody. Not yet.
He's just taking aim.
It's close.
Just taking aim.
Watch. I'll take him out.
I think we need the hard lockdown drill in here tomorrow instead of 6th hour.
I don't want to be locked in here with them. You're always locked in here.
All right. Metals then tend to lose one valence electron. Our 1As do. So that is your lithium, your sodium, your potassium, your cesium. Did I forget somebody? Rubidium. I forgot rubidium in there. I know. We just don't use it much. Cesium and your francium. Now, I want you to take out your lovely orange periodic table that I gave you on the first day of class. Has anybody lost their lovely orange periodic table?
I'm going to
have you mark these up, so make sure that you take out your
first. Not my lovely orange periodic table you gave us at the beginning of the year. No,
Anybody need a new orange periodic table? Nicholas, do you have your orange periodic table?
You are helping freshman. Look what he did there. It got broken. Look at this. His dog ate his homework. A likely story. Look at this. Look at the rescue. Thank you. Freshman.
All right, first of all, I want you to go and mark your stair-step line on your periodic table. So go through and mark your stair-step line on your periodic table. Good. Yep.
What happens when it hits Unu hexes?
It just goes straight down.
Just go straight down?
Yeah, it doesn't matter. We never use those anyway.
Why not?
Because they don't exist long enough to do anything with, and they're radioactive. So All right, you good with that? Now, look over here at lithium, sodium, potassium. Do you see over in the corner where it says +1?
I do.
Okay, that's going to become very important to you tomorrow. Okay, being able to locate those. If you go over to the next column that starts with beryllium and goes all the way down, all of those say +2 because they're going to tend to lose 2 electrons so that they can look like the previous noble gas. Okay. If you come over here, you'll see that your aluminum, your gallium, and your indium have a +3. That's because they tend to lose 3 electrons. Okay. And then we start to muddy the waters over here because we're getting into nonmetals. And we're going to talk about those in just a second. All right. Now, you will also notice that your transition metals, if you look at your D block, that they're kind of all over the place. They got pluses here, pluses there, a bunch of different pluses. And I'm going to teach you tomorrow, the next day, how you can figure out what you're working with there. Okay? Just see that they exist. That's all you got to know right now. Okay? Don't want to throw everything at you at once. All right. You good with that?
What's going on with nitrogen?
Oh, we'll talk about him. All right.
It's like the problem child that always gets in trouble at school. I could not get into trouble. My mom would kill me.
So now we're going to move our attention over to the negative ions.
Wait, I think you missed a slide.
Okay.
Yeah.
You mean this slide
That's it.
that was up there for a little while
Oh.
that you didn't bother to write down anything
I
about?
was looking at my periodic table. I'm sorry.
All right. So when we look at these, we've got negative ions here. We talked about these a couple chapters ago. Last chapter, I believe, we talked about anions.
Yes.
And how these want to gain electrons so that they can look like the next noble gas. Okay. So your fluorine's going to gain 1, your oxygen's going to gain 2, that sort of thing. All right. I want you to write that stuff down and then we'll talk about your periodic table in relation to that. All right. So now if you turn your attention over to your periodic table, you will notice that these have a lot of options. So your carbon and your silicon, you are going to take everything in their box and mark it out except the -4.
So just
Get rid of anything that's not -4 in carbon and silicon. The only thing that should be in their box is a -4 as far as charges. Leave all the other stuff, but get rid of the charges. Carbon and silicon, get rid of everything but the -4. The top number there. Okay, everybody cool with that? Now we're moving over to the next column. The next column, we're going to look at nitrogen. We're going to look at phosphorus, and we're going to look at AS. Arsenic.
my
Okay.
favorite chemical.
You are going to get, are you listening to me? You are going to get rid of everything in those boxes as far as charges except the -3. Keep the -3 on these and get rid of the other one. And for nitrogen, that's a lot. Okay. Oops, shoot. Now we're going to turn our attention to the oxygen column. The oxygen column, oxygen, sulfur, Se, and Te. you're going to get rid of everything except -2. So each one of these, get rid of every charge in there except a -2. And then last but not least, the fluorine column, which is fluorine, chlorine, bromine, iodine, and AT. All of those, get rid of all the charges except -1. Astatine, yep. Okay.
Start saying it like iodine, then it lines up.
Yeah. Iodine.
All right. So now you ask me, Lippy, why don't you just go through and mark all of those off for us? Because they actually are useful in AP Chem. So if you come on, if you sign on for another year with me, I will show you. In fact, they're taking their test today on using those extra numbers for those nonmetals.
Wait, that's not Monday.
Yep, AP.
Ooh, after they came back from, man.
You want to state them?
Yeah.
AP is paced out. It is what it is. Like, I have so many days. I have so many days for each unit, and it just happened to end up like this. So,
Still, that is brutal.
well, they had all weekend to study.
Who wants to study over something? Who would study over 5-day weekend?
AP students.
All right. So, when we look at these ionic bonds, they are going to form between a negative ion and a positive ion. And it's that attraction of the negative to positive that is going to hold these atoms together, or hold these compounds together. So it's those opposite forces that are interacting. Okay? So, for example, when we work with these, okay, we have the same number of electrons that are lost have to equal the same number of electrons gained. So if you're talking about calcium, calcium wants to lose 2 electrons. And if we're going to chlorine, it needs 1. So we would need 2 chlorines for each calcium. And that's how your formulas work. You need 2 chlorines for each calcium. Does that make sense? This has 2 electrons to lose. So you need 2 of these because it only needs 1 each. That's as hard as your formulas are. They're not bad. You're going to be okay with them if you just give me a little bit of time. Okay? Don't get overwhelmed with them. We'll get started with those tomorrow. All right. They form what's called a crystal lattice, which is this strong attraction. Positive ions and negative ions, they're going to form kind of this scaffolding. Okay, so they form this scaffolding. So this is kind of like what that looks like. Now, what happens is that this is attracted to this because of opposite charges. If you apply a force to this, though, like a grinding force or some sort of force to this, what happens is that one of these planes shifts. And you end up with negatives next to negatives and positives next to positives. What do like charges do? Repel. And that's why these tend to be brittle. So your metals have this sea of electrons where they'll kind of spread out and be able to handle that force applied to them. Okay, they'll dent, they'll be impacted by that force, but they're not going to break apart necessarily. You do that to salt, or you do that to any kind of ionic compound, and it's going to crumble. And the reason why is because of these charges coming together and these repulsions that happen. So here are some of the properties of these compounds. You have a high melting point, a high boiling point. You can't take salt and put it on your stovetop and actually get it to melt. You can get it to dissolve into water, okay? But you're not going to be able to get it to melt. Your stovetop doesn't have enough heat to make that happen. Yeah, I'm right.
No, my stovetop gets to 1700 degrees Celsius. Yeah, but if I let go on it to really give it the extra edge.
What would it take to melt salt?
I got to look it up. I got to look up the melting temperature of NaCl.
How hot does that have to be to make it?
Oh, 1700? Yeah, that might do it.
The boiling point.
No, that's Fahrenheit. Hold on. That's Fahrenheit.
What's
Let me
the
see what it
boiling
is in
point?
Celsius.
I'm way over.
Celsius is, yeah, you're way over for Celsius.
Easy. I can boil salt.
What kind of
A good one.
stove do you
A
have?
good one. Yeah.
I want a picture of this.
It's just a tiny little sun.
Libby, what's the boiling point?
What?
Salt.
I said it's just a tiny little sun.
What's the boiling point?
Boiling point is 1465 Celsius. No, I want to know the make and model of that stove.
It's time to boil salt.
They're hard, they're rigid, they're brittle, and they take a lot of energy to break apart. I would have to look it up. Okay, so no, I want to know. I don't believe you, Andrew.
Are you implying that I'm lying?
No, I think you're misinformed.
Wow.
That's a nice way to say you're lying. I think you need to apologize to Andrew.
No, I want more information. I want to know.
Dude,
I want
sounds
to
amazing.
You simply have to trust me.
No, don't trust. No. Miss Libby apologized to
Sorry,
you.
it puts off so much heat.
I'm just telling you that, like, I don't think it can happen. Okay, you have homework tonight. Are you listening to me still?
Yes.
Yes.
7-1 is your homework.
Oh,
Have to be.
Here's melting salt, it says, in a furnace.
Oh yeah. Oh yeah. What's that?
Number of electrons lost must equal number of electrons gained.
Okay.
Hey guys, it's your boy. It's time to melt. What happened?
7-1 is your homework tonight.
Lauren, why don't please come to the student center building, legal please come to the student. Excuse me, to the attendance office. Lauren, legal please come to the attendance
Yeah, let's
office.
put ice on liquid salt.
There you go. There's your liquid salt. Yeah, and I'm telling you, you're missing like some pretty fundamental stuff. So make sure that you're keeping up. And if you've got, and don't blow it off. Like, I don't know if you're going on vacation or what it is, but when you come back, like, it is hypercritical.